How are you?
I'm fine, thank you.
Uh, okay, so welcome to our meeting today. Um, I guess Stefan is gonna present a paper. We sent it out on Slack last week, and you know, it, he'll tell you a little bit about it, and maybe we can have some discussion around the paper. But if you can't think of anything to say, you can always bring something up in the Slack during the course of the week or later on. Hopefully, this series will be a good experience for everyone. So first, I'd like to ask, and I already asked, I think before, are there any issues or questions that people are having? Okay. It wants me to log in to change the size of this room. Let's see. I don't know why it's doing that, but we'll just let me log in here real quick. Are you trying to share your screen?
Not really.
No. Okay, well, I guess we're okay for now. I just got an alert saying that the room was full, but I think we're okay. Can you share your screen?
Oh yeah, sure. Yes, so should I start with presenting the paper first? Or do we discuss the issues?
Not sure. I don't know if maybe I think you may have knocked someone out of the room. Oh, wait a minute. No, here he comes. Jesse. Yeah, are you okay, Jesse? I think he's okay. Well, let's see. So I think we can do the screen. Okay, that's fine. Let's do the presentation first.
All right. Yeah, so then I would start. Hello everyone, I'm glad to have you online today, and today I'm presenting the paper Extended Dynamical Systems Theory to Model Embodied Cognition from Hutton and Yoshimi from the year 2010. Just a background on maybe the authors. I don't really know the Hutton, but I know the Jeff Yoshimi. He's basically the one who's built this wonderful SimBrain. Right, this program for cognitive simulations, and he's been doing it for the last, I guess, it's around 20 years for now. So yeah, and he's basically interested in many things, as you can see on Google Scholar, not just cognitive science, but also philosophy. And well, this paper in particular has also had a really fairly good amount of maths. And also, I mean, not that basic maths, but also some differential equations and stuff. So I guess he can also do this. But right, let's look at it now. So yeah, what's the paper about in general? Topics, the keywords would be embodied cognition, this representation battle, between internal and external, where, as we will see, they also provide some or suggest some solution that would incorporate both representations while doing the simulations of an agent of the embodied cognition, basically. And of course, studying the behaviors of the agents we kind of try to simulate in this embodied cognition simulations. So yeah, they kick off an introduction starting, just giving some insight in the state of the art, and also in this internal representation. So what's happening inside the agent and how that influences his behavior, as opposed to external representation. So how does environment influence the behavior of an agent in it? And they say that most people up to the moment, they've been doing it. So most of the cognitive sciences, they would first really separate these two internal and external representation. And for each one of those, they would introduce some dynamical system, which by definition is a map phi, which provides for each state and time, it provides the next state. So the next point where the agent will go. And so it describes the behavior, either the behavior of an agent or changes in the environment, if we are speaking about external representation. Yeah, so that's how people have been doing it, just basically taking a map between states and they described behavior this way, or maybe, behavior of the system, not only an agent. They were describing it with dynamical systems, but the authors, they argue that first, these dynamical systems are too closed for rich worlds of, agents and environments, which could basically have a really big interplay. Of course, it also comes from the fact that we have these two separate representations and two separate dynamic systems, right? The internal one for the agent and the external one for the environment. And they, like in the traditional approach, they don't really collate, so they don't influence each other just because they're separate. And so dynamical system representation of an internal state of an agent is too close just because, it doesn't have this openness of also involving the environmental changes in the changes of internal representation of an agent. And so they also say that, they find that some cognitive scientists in this sphere, they have been using mathematical formulations that were not really rigorous enough to work with this, to use it as a tool to investigate the behaviors and changes of systems. And also they say that, the traditional approach, or maybe also this unexact mathematical formulations, they give birth to some strange phenomena like, for instance, moving fixed points, or, some moving orbits that shouldn't have been there, but they are because dynamical systems approach is extendable. And so what they basically do, they extend this approach. They call the new approach open dynamical systems. The main idea of this approach is basically to give an interplay to the dynamical system of an agent internals representation and of the dynamical system representing changes and states of the environment in which the agent is at. And it's a figure from the paper. It looks somewhat like this. So, right, we have on the left bottom figure, we see the dynamical system of an agent without involving, so representing some paths, so-called paths that agent goes in his, so to say, just on its own without being influenced by the environment he is in. And then it goes with the transformation sigma. He's been kind of embedded in the dynamical system. So in the system of his environment and him inclusively. And then with continuous deformation phi big, his own internal system has, which has been embedded in the whole total system, including him and the environment, is being influenced by environment. So on the right top graph, we see how his paths are influenced in the total dynamic system using this continuous deformation phi, which is basically, so to say, force or changes that environment appeals to him. So how environment does change the agent. And then with transformation P, having this total dynamic system with changed agent paths and states that he has in this environment, we use transformation P to kind of project his paths from the total representation, right? So including him and his environment, back to his internal state space. So we basically we can go on this pipeline from sigma, phi, and p. We can see how really the environment in which agents influences his internal state and his internal paths, as well as we can see, of course, how the two interplay, right? So in the whole dynamic system, which is called here phi theta, phi theta, we can also see the interplay between agent and his environment. Right. So having that, there basically, of course, there's they then start to analyze, some cases we will have with our paths. So basically, how it can look like. What do we notice? They notice that the same as you maybe know, the same story as with this harmonic oscillators. We also have some, so to say, patterns of various paths, and paths also group. So we also have some attractor points which kind of get a lot of paths or a lot of lines around them. We also have repulsor points which are not really that likable from the agent points of view, apparently. And we have then some, some groups of lines and some groups of paths which we say are isotypes. So basically, their typical behaviors, what also stands here in the first line. So, for instance, they argue that this whole framework of open dynamic system is really useful for representation analysis. So where we have an agent and we know his states, paths, and how it's embedded in the environment, we kind of can investigate his typical behaviors, or so to say, typical paths that he goes. We call them isotypes because they are grouped together, and therefore we can kind of boil down the whole big complex system of possible paths of an agent that he goes just to some typical isotypes, groups of paths which we then kind of label somehow, and therefore we have done a representation analysis of an agent. Yes, and it's also argued, just to put a note on this statement, that kind of these paths that we have, or this path states that we have at the end, they really represent what's going on in the agent and maybe also in his environment. That's the assumptions being made. Of course, it's also then worth to say that when we know that, we also are sure that it should be constructed somehow. So these paths, they really should stand for what's really going on in agent and the environment, which I would like to discuss later in the examples that I'll just provide. Right, so this is also a nice figure. Here we see an example of possible states and possible, environment changes and states of the circle world, so to say. The circle world is basically nothing more that a circle, and we have the agent, which is painted in gray. He's also on always on one point at the circle. He's always here, right? And we also have two objects that are rotating around the circle. And so it's argued that, yes, this agent, he also has two sensors, which is basically really similar to what we do with Braitenberg vehicles, right? He has two sensors, one for each object. And these objects are moving, and we are interested in how they influence the agent and his sensors, and therefore also his internal state just by moving around the circle. And we kick off with saying, okay, so we can determine the location of both of these objects just by providing their angle to some horizontal line. And that's what basically we see here. We call these angles R1 and R2. And we just look at the graph. So how does it change by objects moving, and depending on how far are they from each other. So how different are the angles, R1 and R2. And in this case, it's of course also noteworthy that both of this agent move with the same speed. Otherwise, it would be somewhat complexer, but here we have just a bunch of diagonals, right? And these colors, color groups, these are exactly these isotypes then, which we've talked about. So basically some groups of paths there that produce really some similar behaviors, which we can then call typical. So for instance, this green bunch, it's some kind just moving, moving here and there like this. Red shades of red produce some circular behavior. We see that bluish ones, they produce some triangular behaviors, nevertheless staying on the sides of X1 and X2. That's just a basic example of some path analysis and separating some typical path groups of an agent in the context of interplay of an agent, here being this gray dot with two sensors and just two similar objects rotating in the circle, where so basically, I mean, the most simple example, but still, then we can see that it produces some interesting, nice results and some really separate behaviors in the agent. Yes, so basically they follow up with some real-world examples. Then they also try to look at this Otto and I guess it was Anna. Yeah, let's say it was Anna. So Otto and Anna problem. There's this man Otto who has an Alzheimer's disease, and he tries to find Anna in the museum. Somewhat that like Anna told him to find, but the problem is that Otto has Alzheimer's, and so he doesn't really remember. And we can also use this framework, they say, to look at the behaviors of people having Alzheimer's disease, how they behave, and maybe also provide understanding what's going on there in their minds. We can also provide some help, like identify weak places, and maybe work with these paths that could be fixed by intervenience when we know where exactly do we intervene there. They also say there are some examples and some further examples of salesmen sailing on the ship, and the relationship between one individual salesman and the whole ship crew, and maybe also the sea, and how this should influence the ship planning, and also maybe speed, maybe the direction of the ship. That's of course all very interesting, but there are some questions then. So basically they conclude with the proposition of their framework as being somewhat more integrative than that they used to be. They say that open dynamic systems approach is really then so it incorporates multiple aspects, being agent and behavior, and agent's behavior, and the world's behavior. So also environment's behavior, which hasn't been done yet, they say. And they say that this framework could then be useful and maybe yield some good results in representation analysis. Right, so I would first kick off with open questions that I have just maybe to give you a start, maybe to think about what we could also discuss, and then I would also say a point about what I maybe find, somewhat what I found maybe not that clear for me in this paper. It would be also glad to discuss this, of course. So the questions to the authors, my questions to authors would be, first, how do we compute phi? So this big phi continuous deformation, it was nowhere clear where does it come from, right? So it should be some kind of representing the interplay between internal system of an agent and total dynamical system, or maybe environment dynamical system where agent is embedded in. But it was nowhere how do we really compute this, or like how did we determine what the form this phi has, and what is the meaning of the degree? There are also some degree of this phi. So they basically say, okay, if the phi has the degree is a rational number between 0 and 1, and they say, okay, if phi has degree 0, that means that we have just a pure dynamical system with embedded agent, but without any deformation. So we basically have kind of pure agent embedded in environment, but without environment having any influence on him. And if the phi has the degree 1, we have kind of this total dynamical system phi tau, which we see on the right, which is kind of totally or fully deformed by some environmental forces or environmental states or things happening there. And so they say, like, we have continuous scale between this 0 dynamical system and degree 1 dynamical system of phi, but it's not really clear for what's the numbers between 0 and 1 stay. So that was my question, like, how can we really give it any meaning in our application, in our applied analysis using this framework. And of course, the third question, it's about scalability of the whole approach. So we know that usually there are a lot of states and in the agent, which agent can take in his internal representation, and I would arguably even more states that environments can take or be in, based maybe also on how big the environment is. And of course, it raises a question how tough or maybe how expensive it is computationally, for instance, to really look at both of these sets of states of the agent and the environments, and how doable it is to learn it, or maybe to construct it first. So that's also a question. I would say the biggest one. Right, so that's really important if you want to apply this toolbox. We kind of like have to have means for that and have enough power, computational power, for this thing. Yeah, and I would say there are, of course, like also two weak places that I maybe. Also influence the impact or the how interesting the paper is. There has been some there have been some really mathematical examples. So, for instance, this one, it was pretty mathematical. Like we have some really abstract objects, and they are moving, and we have the mathematical formulae, but there it wasn't kind of really applied to the real world. So there was just some ideal world objects, some ideal objects without having, they didn't have any friction, for instance, or they didn't have anything around them. They were kind of separated still from the world. And then they provide kind of these examples with this Otto, who has an Alzheimer's disease, and this sailor ship problem, where they don't basically give any math explanations or some kind of system to it, but rather just describe it more in a philosophical manner with words or stuff. So basically, I missed a little bit the connection between mathematical and, so to say, real world explanations and examples. So it's still not yet clear for me how to apply this framework to real world problems, so to say. Yes, it also, the second statement, it's not, it was not very clear why open dynamical systems are really open. So of course we have this environment influence, and still it's which greatly opens the possible paths that the agent has, but it's not really clear whether it's enough to call this dynamical systems open now, just because we combined two closed dynamical systems. And the third and the last one, I would like to end it with the fact that their examples, none of them was based on real data. It goes once again into the application of this approach or of this framework. They haven't provided data to anything, so it also goes to this states sets. So, you can't also really answer this question now, how tough it is to really learn all of the possible states of the agent and the environment, just because they haven't done it yet. Yes, so they don't provide any evidence to it. Yes.
Well, thank you. That was very good. I think Jesse had a couple questions here. So if you see them in the chat window. Let's see. First one is isotypes are group typical behaviors. Do they mention how that grouping happens?
Yeah, I couldn't tell if it was like an actual set of behaviors or if it was just their kind of. I saw later. Eventually, showed the diagram where it was like the angles and the colors as kind of representing. Okay, you're having this kind of behavior within this range of angles. So I don't know if they kind of just meant that, or if they meant anything else besides that.
Sorry, once again, what is the actual question? Did they mean?
What's their criterion for grouping? Like, how do they?
Yeah, it comes. I would also maybe show you the figure just in the paper. It comes from the argument that, in typical dynamical systems, we have kind of this lines which are, I guess they call them exceptional, right? So exceptional orbits, and they define or divide two bases, two faces of other orbits, right? So they kind of also emerge this from this parallel to the dynamic systems, to just usual dynamic systems. So basically, I just called it behavior just because it looks similar, right? So it's something typical which unites like many possible ways to do it, but they don't really call it behavior, I guess. Even they just say that there are some groups, right, which are isoform. How they divided them, I guess, basically having this exceptional orbits first, or exceptional paths in our scenario, and maybe also looking at what's happening there with x1 and x2. Right? So also by shape they divided them.
Yeah. I take it from this talk that I hope it shows you how everyone thinks about mathematical models as being precise, but I hope this shows you kind of how arbitrary it actually is sometimes. So sometimes, you talk about like different parameters that you come up with, and you can show a good theoretical result, but then what do you actually connect that number to? Is it connected to anything in the real world? And so it's like, there's this plus again with like equations, setting up equations, having a formalization. Oftentimes you'll take like a symbol and you'll use it to represent maybe something very broad or something very specific. There's no real, in some cases there's no real difference between the two. In some models, they just kind of use a parameter for something, and then is that the best way to really model it, or is it just something that works mathematically? So I mean, those are things I think this paper kind of brings out, but probably any paper you'll read brings out that point, is that it's quite arbitrary actually how we do this sort of representation. So Jesse had another question about modeling environmental behavior or its states. I wonder what they suggest about that.
You might not be able to answer that very much, but it's something that it did come up when I saw that.
Yeah, exactly. So basically, I would say, this here in this model, I will show you once again my screen.
Okay.
Thank you. It was exactly this phi big. So this continuous deformation, it stands for kind of what influence or how do agent and its environment interplay, right? And if we take just a separate environment, I guess it was not really interesting for them first. So as you see, like we come from agent dynamical system and we go into the agent dynamical system just by letting environment influence it, but we don't really look at environment big and deep enough. But I mean, as far as I understood from what they've written, the environment is also a kind of dynamical system with its own states, with own states set, and this phi function, which gives a set, which is like state, which will go up to state. So it's just a traditional dynamic system, the environment.
Okay.
Yeah.
Z, do you have any questions for Stefan?
Okay, I also actually have a suggestion.
About the Hope field dynamics. He's still not clear on that.
I mean, this example with like this Hope field function, it was one of the examples, I guess. Is it about the paper itself? So the Hope field, as far as I understood, like they first took just a usual, so to say, vanilla neural network with, I guess it was backpropagation, but it doesn't really matter. So, and then they just took some more complex neuron model. So this Hope field part, and so it was just basically model of neuron activity they were working with in examples, one of them.
Okay, so thank you. Were you going to say something else? I can't remember.
Sorry?
Oh, were you going to say something else? I thought you
Oh,
were.
yes. I would also, these parts with the complexity of learning the states of the agent and the environment. I just thought that maybe here, if we are to apply it on some real world problem, we may be not able to collect enough data for like to really just construct as agent and so the possible states of worlds and the environment ourselves fully. But then we can maybe just collect some part of data, part of states. Notice run some machine learning stuff and generate some more possible states. So, just maybe that would reduce the complexity of the problem, what I've thought about.
Yeah. So, in the other group I work in, OpenWorm, there are people in that foundation who do stuff with, they look at C. elegans, the worm, and they look at movement video. So they take video of the worm moving, and the worm has a number of stereotypical movements and behaviors. And so they actually have a lot of data in terms of like video that they've used machine learning algorithms to segment and parse. And then from there, they apply models. That I don't think they're dynamical systems models, but they use different models to sort of define different states of movement. And so they've been doing this for a while, and they have quite a large library of video and, in different contexts. And so they've been able to define movement, movement states. But even there, you have a lot of, things between states, intermediate behaviors. So it's even in a system like that where they're very stereotypical behaviors already, it's very hard to do. So I think this is a good paper to present because it's really does bring up a good number of issues, and we'll be in the coming weeks when other people present, we'll be talking a little bit more about that. So now I'd like to go over the board real quick and some of the other issues. How was everyone's week in terms of coding and work? Have you run into any problems or things going smoothly? Good, thank you. It's going well. Okay. Okay, Jesse. Yeah, we talked about that, but yeah. And then Stefan, are you doing things going well?
Basically yes, and like the basic simulation is already ready now. But of course, there were some troubles, I must say, with this JavaFX. So basically, I've underestimated the complexity of the task to run to build a GUI with all of this, frames changing and shapes changing their coordinates, maybe also their properties. And I think I've also overestimated the abilities of TornadoFX to be able to build some kind of really applications with constant rendering. So I guess TornadoFX is really made mostly for business cases or business purposes where you have some kind of tables, some kind of dialogues, maybe stuff that you fill out, some forms. So now I had to work with JavaFX, which is underlying the TornadoFX extensively, and of course it was also pretty challenging, I must say. So I've rewritten the code a bunch of times. Just because I didn't understand well how it works in the framework, first. So it's been challenging, but I guess I have a better understanding of the framework now, and I hope to finish this basic simulation as soon as I can. Yeah, but I guess I will do.
Yeah, it's good to get all the kinks out now. Like if you have any problems with working with a platform, it's good to find out now instead of like down the road where, Okay, so let's go to the board. Let me put the link in the chat window, and then go to that repo, and then we go to the projects tab, and then we go to group meetings review, and then we have our tasks, and we'll go from done to the left. So, okay, we have a lot of this stuff is already done, exchange proposals, and then this was specific to Stefan, get in touch with SimBrain developers. That was Jeff Yoshimi, who you mentioned in the paper. Work on presentations, so we're on track for that, and thank you, Stefan, for a good presentation. And next week we have Jesse, and then the week after we have Ziyi. And if you have any questions about it or issues, let me know on Slack. But I like what Stefan did in terms of a presentation. So if that's a model you want to copy, that's fine with me. Okay, then we have Jupyter Notebooks documentation. So is everyone set on their documentation? Any problems with it? Okay. Reason I ask is because my other group, they've been running into small problems with it in terms of they're a little bit more diverse in what they're using for documentation. Like they're using Colab notebooks as well, and so they might be having some technical difficulties with those. But again, we want to keep all of our code, in one place, and we want to keep it, annotated and documented. Okay, we did the set of presentation schedule. So present papers is in progress, number 7. Number 4, share resources and implementation ideas. We've been doing that. I can't remember if there's anything else we need to work on there. I don't think so. But just to remind you. Setting up programming environments. I think that can be put and done. And then we'll keep this number 4 open just in case we need to do any more sharing. So now to do. That's on the left. Issue number 13. And this is for Stefan. Researching potential issues with building block method. I think we talked about that last week.
Yes, right. And I guess it wouldn't really work out that well, and especially, not in Braitenberg Vehicles. The Jeffrey Yoshimi, he's also replied back to me, citing him or quoting him. I say, there's the old saying, I think, due to von Neumann, that with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk, he says. That is how Braitenberg Vehicles see to me. Even just tweaking a few of the parameters with such a wealth of behaviors, and there are many other things that could be that would leave constant, right? So basically, I have a strong feeling that just a small change in the parameters. So it's not that function is not that step as we would like it to be, I guess. Yeah.
Well, okay, yeah, just keep thinking about that. If we have, I just want to make sure that you're aware of, you're on top of the method and that we're not running into any serious problems. And that goes for Z and Jesse as well. If you have, just to think about the problem sort of maybe a step ahead, like what kinds of problems am I going to run into if I try this method? If something seems uncertain, to sort of ask questions, because it may be, because this is not and there's no right answer here. This is research. So we just try things, but we don't want to go down a blind alley. Yeah. Okay, so sure. Number 12, and this is for Z. The review components of model. I think this was about a public review or that we talked about when you presented your presentation, that we would like to, as you sort of implement parts of the model that you propose, that you kind of, give them, let people review it and make sure that, everything makes sense, that everything's coming together. Have you had any more thoughts about that? Okay. Focusing and implementing the innate parts and stimuli. Oh, it's okay. Yeah. So I mean that. So that, I guess we'll leave that in to do. And then I don't know what we do with number 13. Do we leave it in to do as well? That was Stefan's issue.
Yeah, we can leave it in to do because I'm still thinking about it and about this approach.
Okay. And then we talked about number 11, reviewing John Holland's paradigm. And that was, I think, just the basic laying out of a genetic algorithm, how it's supposed to be implemented. So that's to do as well. I think people, we're not quite there yet, or okay to do for me. So it's, that's something that if you want to discuss it further amongst yourselves or you want to ask me questions, please do, because I have, I can give you feedback on it. And then community evaluation, which again, number 10, that was something that is maybe a bit down the road. So when we get, parts of the project to a point where we want to have people evaluate it, we might actually do that in the meeting. We might actually do a short demo to show how things work, to bring up questions. That's just keep that in mind so that 1 week we might be able to do that.
Yeah, that will be also, of course, great repetition for, gay tryout before the conference. And this demo at the conference just to demonstrate it online to some other people, some community. Yeah, that's a great idea, I find. Yeah. Totally.
Okay, so that's all the issues that we have right now. Are there any additional issues we need to put on the board? Can we think of anything that maybe in the next week or two?
Not really, no.
Ziyi or Jesse, can you think of any issues that we need to put on the board? Yeah, you can put them on any time. You're a editor on the repo, so you can post an issue either to GitHub or even put it in Slack, and then you can transfer it over later. So yeah, we should be adding issues continuously when we think about them. Okay, yeah. No, you can do it anytime. Yeah, I mean, it's probably good because once you remember it, you forget it if you wait, and so it just minimizes that. So if you have anything, put it on the board. Right now, I'm just gonna let you kind of think about it and then, put them on the board during the week. So I don't know how you want to manage that. If every part of the project should have an issue or not. I guess we're taking the latter approach where we're just kind of like putting issues up as they kind of come along. But you'll find that some people will put every little thing as an issue, especially if you're working like a coding project. They'll have like different bugs will have their own issue. I'm not quite sure how to phrase this, but I think I'll look more into modeling some environmental behaviors and general impacts. Okay. Okay, well, I mean, we can, yeah. Okay, no, files to repo. Okay. Oh, about putting things up in the repo. So, I mean, I would like to see some pull requests or some, putting files in the repo just simply to monitor progress and to get, a sense of, what's going on with your projects. And then, maybe that people can look at what you're doing. I mean, I don't know how public you want to make everything, but, I think definitely, like, if you get something to, a point where you want to share it, then you can put it up there. I would encourage you to, in fact, because, we can get feedback. We can, I can look and see more directly at what you're doing in terms of code and implementation and give you some feedback on that. So it's always good to have it out there. You know, you don't have to put everything the moment you like put it on, like put it down on the computer, but you know, you can, you know, I mean, cause I know people are a little self-conscious about like what the code looks like or what, you know, but definitely I think once a week would be a good sort of, you know, rate of putting something in the repository. You know, maybe we can review it at the meetings. That gives you some feedback, I think. Okay, yeah, so, yeah, no problem.
So just a question on that, on putting things in the repository. I basically haven't done this up to the moment because I kind of understood the repository to be really this, you know, this release place where we show something to people. Is it like that, or should I also put something when it's when it contains bugs and some?
I think probably the latter. I would let me show you how I have it set up now. Okay, let me share my screen real quick. If it works here. Let me go to this. Okay, you can see my screen now?
Mm-hmm.
Okay, so I have the repository set up so that we have the README is just basically information about the project. And then I have different people's names here.
Mm-hmm.
And so if you can go into your name and then issue a pull request there or upload the files directly, that would be a good way to do it. And I think a good yeah, like I said, a good pace of that is maybe once a week. Put a release up. I mean, it doesn't have to be like, you know, like just a totally raw working space where you're kind of like just throwing files up in an unorganized fashion, but just to have something that, you know, we can look at and, you know, kind of keeps you, and it helps you organize as well because you'll have the files in one place and you'll be able to sort of see where, you know, monitor your progress over time. So you'll have your, you know, each week you'll build on the files that you upload and you'll have things there. And then you'll see that everyone has their own folder. So you know, you push things to those folders. And then there are a couple folders where we have some auxiliary information. Like I have some Connectome data. I don't know how useful that'll be, but you know, we'll put things like that in there. Maybe it'll be helpful to people in terms of like formulating their next steps. I didn't talk too much about actual data from you know, from real systems, but that is available. So, but that's down the road, and we can talk about that. So, okay, I think we're coming to the top of the hour. So, thank you, Stefan, for presenting. And I look forward to Jesse's presentation next week and then Ziyi's presentation the week after. And if you have any questions, let me know. I think that, one more thing I have to tell you. Next week will not be Saturday. I don't know if this is going to be a problem for people, but I may be available on Saturday morning, which is Saturday morning here. But I don't know. I may move the meeting to Sunday because I'll be traveling in the latter part of the week. So if we met Sunday at the same time, would that be a problem for anyone?
That's okay.
Not for me, no. It's okay.
Okay.
For me as well.
Ziyi or Jesse?
That's okay for me.
Okay. Is that okay, Ziyi? Okay. Okay, so then we'll meet at the same time on Sunday next week.
Okay.
And then everything will be the same. I'm gonna be traveling, and I don't know what my Saturday schedule is gonna be like, and you know how that goes. So yeah, and so everything else during the week will be fine, and we can, hopefully I'll see some of you on Slack and or on GitHub. And we'll see what happens next week. I look forward to. I like the conversation on the papers. As you can tell, it's good to people get some. It'll get some thinking going. And if you have any thoughts about that, just put it in Slack. So, okay,
All right.
guys. Thanks a lot for your attention. Have a good week.
Thank you. Have a good week.
Okay,
You all.
thanks. Yeah, bye.